Hello. Good afternoon if you're on the East Coast, or if you're on the West Coast like me, good morning. As Jalen said, I'm from Inktank, and I'm about to talk about Ceph. So Ceph is an open source distributed storage system, and we recently just did a rebranding of Ceph because we launched a new company called Inktank, which is a support and services company around Ceph. So many of you may be familiar with Ceph, but aren't familiar with the sort of visual look of Ceph that we have now. We started a company because Ceph is getting to the point where we need to figure out how to start helping people deploy it. So this is the Ceph stack. It's got a lot of different parts and a lot of different components, but it's all based on something called RAOS, which is the Reliable Autonomous Distributed Object Store. On top of RAOS, we built a series of applications that allow you to use the distributed cluster in a few different ways that I'm going to go into more detail on. But first, I think it's probably best to start in the beginning. And I have this nasty habit when I do presentations of going all the way back to the beginning of like humanity and trying to make it mean a lot more than it does. And that's what I'm doing here. And the beginning of information storage. I think the first example of how people stored information was probably cave paintings. You know, it's how people recorded history and recorded stories and things like that. We've come a long way since then. At some point, we figured out how to write. And writing was kind of like cave painting, but a little bit better. You could put a lot more information inside of a book than you could on a cave painting. So, I mean, already we've noticed in human history that we've outgrown the cave, and now we're beginning to fill up books. And, you know, like about 1,000 cave paintings could fit in a book. I mean, I don't know. It's really difficult to say, but that's about the right ratio. And I'm mentioning this to you because later on, as I kind of move throughout the history of storage, we see this sort of ratio happening all the time, where we increase the amount of information we can store by a large factor. So people began writing a lot and capturing a lot of information. And I mean, so much so. But the problem with writing is that writing is kind of time-consuming. It takes, I would call it, in modern terms, we'd call it a really low bandwidth, media, right? Because it takes a lot of time to write, it takes a lot of time to read, and accuracy is not so great. I mean, I can't read half the words on this page. So people figured out how to industrialize writing. So how they can use machinery and how they can use technology to make it so that the written word was more effective, more legible, and more prolific. But at some point, something really magical happened. We had so much information that we outgrew the book and we outgrew the library. And so, fortunately, we were able to come up with something called magnetic tape, which is not really the combination of magnets and tape, not really, but kind of. And again, we see this ratio where 1,000 books can fit onto a single magnetic tape, which is again, you know, an exponential increase in the amount of data that we store and the amount of data that humanity has collected. So this new method of storage was mechanical in nature, right? It no longer was something you could pick up in your hands and read, just human being to device. You required technology to allow you to interface with the storage that we've created. And it was kind of the first time that we noticed that we started with a nice simple interface between human being and rock, you know, and I'm being a little bit, you know, cute, and then human beings began to interface with ink and paper, but then we saw a huge divide when human beings began to interface with their information with an intermediary, which is the computer. And that caused a lot of technology to need to be built. So building this technology, we're computer programmers, right? So computers need people to work. For the first time in human history, we require a specific type of person whose entire job is figuring out how to allow humanity to interface with its information. So we have this thing in the middle now between the humans and their information, and the other thing that happened at the same time is that we started storing information in zeros and ones, in binary, or in some other non-representational form. So this picture of this, I don't know, this frog on a dune buggy or whatever it is, ends up being a series of ones and zeros, which we can't read without the help of computers. About this time, that's when throughput became really important. When we had computers reading and writing our information for us, suddenly it mattered how quickly that happened, right? Latency began to matter. The rate of reading and writing began to matter. That sort of thing started to matter, and that I don't know if that led to the invention of the hard drive, but I suppose hard drives must have come around at just about the right time, because we also saw again a 1,000-to-1 jump between magnetic tape and hard drives, and I think that it changed the world, right? Because hard drives are a lot better than tape, and today, in modern terms, you could put the same chart up and say that solid-state disks are a lot better than spinny disks. But at the time they came out, it was just this outrageous invention. But because we invented technology that allowed us to store another sort of level of measurement of information, we've gone from kilobytes to megabytes to gigabytes. It became really obvious that we needed to have some kind of technology that allows us to organize our information. So that's kind of when we saw the emergence of file systems. And file systems are a hierarchy of information with directories and nodes and things like that, and it allows you to organize your information and also store a little bit of metadata. For example, if my frog picture were a file, we'd know a few things about it, like it was owned by me, it was created on August 12th, it was last viewed on the 17th, it's about 42 kilobytes, and it's readable by everybody and writable by me. And these are the permissions that we have in this file, which then gets positioned into a tree, right, in an absolute way. So this allows us to start to store even more information than we did before. So you're seeing the trend that I'm trying to paint is that humanity keeps inventing new ways to store information and then keeps outgrowing those ways, and that always happens. That's going to happen forever unless somebody builds technology that is truly infinitely scalable. So again, humanity outgrows the hard drive. We just had too much data. We can't fit everything we need to fit on one hard drive. And I'm not talking about all the information for humanity. I mean, my movies won't fit on a single hard drive anymore. There is no hard drive big enough to store all of the data that I personally have collected. So we needed to figure out a way to have storage of something that was bigger than one hard drive. So now we're figuring out how to have a computer interface with multiple disks. So we have a human being interfacing with a computer that's interfacing with multiple disks at the same time. But that didn't solve every problem, because it's not just my movies that need to be stored. What if my friends want to watch my movies, or my family wants to watch my movies? We need to figure out how to allow multiple people to interface with multiple disks through a computer. So computers are getting smarter the whole time. They're getting more intelligent because they're having to deal with more advanced situations. And actually, it looks a little bit more like this. It doesn't look like this. It looks a little bit more like this, because you have tons and tons and tons of humans interfacing with tons and tons and tons of disks. And guess what? We've found another bottleneck, right? I mean, this computer in the middle is looking awfully tired at the moment. So the next sort of big boost in innovation for storage was distributed storage, which is multiple people interfacing with multiple computers, and each of those computers have multiple disks. And it doesn't show in this slide, there are multiple disks on each of these computers. So we've gone parallel at this point in storage to solve a problem. At the same time, we've realized that not everybody needs this tree anymore. Not everybody needs to organize their data hierarchically anymore. And so some people actually just want to store objects, and they can be any kind of object. It could be a picture of my frog, but storing it as an object instead of as a file gives us the ability to have sort of some more arbitrary data associated with it. And even more so, it allows us to not have to put it into a tree. And so an application or a human or whatever is interfacing with the storage system can just store an object in the system, and the computers figure out where to put it and how to find it. And the computers also figure out how to keep track of all of the extra information that goes along with that object. So that's object storage. At the same time, something else kind of magical happened. And I know I've gone from cave paintings to object and block storage in like 4 minutes, and it's a little bit jarring. But something else happened where if I had a bit of information on a bunch of different computers on a bunch of different disks spread out and distributed, I can take that information and assemble it into a disk that then is used by a computer. And this is what we call a block device. And in the case of, CloudStack or any of the sort of cloud platforms, you're really looking at powering virtual machines inside of a giant container to do this. So throughout history, sort of concluding my going back to the beginning of time intro that I always do, going throughout history, we started with painting and writing in computers, and we're working all the way forward towards, this exponential growth in the amount of data that humanity is storing, and we think that Ceph is the answer. And that's what our perspective is. We think it's one of the answers out there. So as humans began to interface more and more and more with these multiple computers accessing multiple disks, it became obvious that this was something that could become a business. So what people did is they took these clusters of computers and disks and they productized them into appliances. And there are lots of different options for appliances out there, but humans interface with these appliances instead, and it's a much simpler way to interface with a complicated network of computers and storage. And these storage appliances, they're real things. They get put on trucks and they get shipped across the country and they get bolted into a rack, and you plug power into them and they do a thing for you. And they're actual devices. They're actual things. They're not software. They're hardware. And the largest manufacturer of these devices has 6.4 million square feet of factory space. And so it takes a lot of money to make these devices, and these storage vendors have a lot of bills to pay. They have a lot of costs. They have a lot of research. They have a lot of capital expenditures that they need to justify, which means that storage appliances are kind of expensive. And they're also expensive because you're not buying software, you're buying hardware, you're buying a consumable. And so it's a somewhat expensive way to buy technology. At the same time that started happening, I guess in the last 15, 20 years, technology also increasingly became a commodity, just like wheat or corn or anything else, soybeans as a commodity, and that means that the prices fluctuate all the time on technology. Hard drives go up in price, hard drives go down in price, processors go up in price. Well, actually, they never go up in price. They go down in price. But there's a certain amount of fluctuation due to the commodity nature of computing, and sometimes you can buy computers cheaper than other times. But if you buy a hardware appliance, let's say I buy a petabyte of storage with a hardware appliance, and it's with a proprietary appliance vendor, a really well-known appliance vendor. It's going to cost, I don't even know, like $14 bazillion. It's just a number, right? It's going to cost a certain amount of money, right? But then when I go to buy my second petabyte of storage, choosing the same storage vendor, it's going to be another $14 bazillion, right? Because I have to buy the same thing again, and I have to buy it usually from the same vendor, and I have to, I have a little bit less flexibility in price than if I were to build it myself, for example. The other thing that is challenging about storage appliances, especially as it relates to the cloud and this ever-increasing demand for storage, is that appliances are kind of, by definition, old technology. And I'm not trying to be pejorative here or critical. I'm just saying that by the time a company assembles all of this hardware and tests it and makes sure that it's secure and makes sure that it works with all their other products and that sort of thing, you have a bit of a runway. And so, for example, this is the list of the fastest processors available today from CPUbenchmark.net. And the flagship product from the largest storage appliance vendor uses this chip here. And it may be that it doesn't need any more than that chip. And it may be that it uses that chip because that chip is the most reliable or whatever. But the truth is that it's not something you can change. So there's a bit of a black box nature to these appliances, and there's an advantage to that in that it's a little bit more convenient, I think, or a little bit perhaps back in the day it was a more reliable thing because you could test this unit as opposed to testing 1,000 different parts. But they're kind of black boxes. So if you, for example, wanted to pull out a compute node and put in a faster, bigger compute node to deal with some sort of hotspot, you could do it, but you couldn't do it with everyday hardware. You couldn't just go to Fry's or, whatever the electronic store is around your house and buy a better processor and put it in. It's not that kind of flexibility. And similarly, if you're a human of subtype developer, subclass developer, and and you want to interface with this appliance to make it do something that it's not designed to do, that's not good. And really, the only option you have at that point is to go back to the vendor. So I think the perspective of Ceph, the Ceph project, is that the world needs a storage technology that scales infinitely, absolutely infinitely, because we understand that our requirements for data storage are going to scale infinitely. So we think that the technology should scale infinitely as well. And we also think that the world needs a storage technology that is software-based, that doesn't require an industrial manufacturing process behind it. We don't think this problem gets solved by putting more technology onto trucks and trains and planes and bolting into racks. Well, we do, but we have a different perspective. So this is Sage Weil. He's the co-founder of DreamHost, which is a company that has invested in Ceph. He's the inventor of Ceph, and he's the CEO of Inktank, which is the company we spun up to do services and support around Ceph. And Sage had a vision, and his vision was that he wanted to build a storage solution that was consistent with a certain number of philosophies and design principles. And the first is that he wanted to build it open source. And the reason is because he felt that the technology that we're building has the potential to change the way people look at storage and change the way people feel about storage, and that open source is the best way to spread ideas and to spread adoption of technology. He also believed that we needed to be community focused, and as the community guy, I'm very thankful about that. It makes my job kind of nice. I don't have to argue so much with people who don't get community, which is really good. But the real motivation is that all of us are smarter together than we are alone. You've heard that a million monkeys with a million typewriters doing complete works of Shakespeare. I think we're kind of proving that with the internet, that actually happens. I think that the more people you get involved in a software project, the better it becomes. And this picture actually is kind of interesting. This is my LinkedIn InMap, which is a list of all the connections I have on LinkedIn, showing how interconnected we truly are, that all of these people that I know would know all of these other people that I know is really fascinating. And he wanted to make sure that whatever happened with Ceph was done in a way that was community-focused. And the other reason that's important to be community-focused is that Ceph, the technology, doesn't belong to Sage, it doesn't belong to Inktank, it doesn't belong to anybody, it belongs to everybody. And just kind of like a forest, we all have to take care of it, we all have to pitch in and do our part. And so, for example, if Ceph doesn't do something that you want it to do, we encourage people to make it do that thing. It's open source and it belongs to everybody. So that's a really important philosophy as well. On the design side, we wanted it to be scalable. I'm going to take a bit of it. Well, actually, we wanted to make sure that it was appropriate for a world where we have more data than can fit on a cave wall, more data than can fit in a book, on a disk drive, on a single computer, more data that will fit in a room. We want to be able to have a technology that can expand beyond that and truly be infinite. We also felt kind of strongly about having no single point of failure, and this is very similar to scalable, but it's a little different. A lot of storage solutions scale, but with a single point of failure. And the way our philosophy is, it's that if you have a truly infinite storage network of millions of disk drives, something's going to be failing all the time. You can't afford to have something fail that is a single point of failure. And this is the tangent I was talking about. I was a bit lost, but this is kind of I know it's kind of a startling picture. This is a banana slug, and a banana slug is the mascot of UC Santa Cruz, which is where Sage got his PhD and studied storage and invented Ceph. This banana slug is also in the same genus as the cephalopod, which looks like this, kind of. And this is the original logo for Ceph that we had before we decided to rebrand. and it's still our mascot in many ways. But you'll notice that it's a good metaphor because an octopus has multiple arms, 8 arms, so obviously it has replication across its arms. It has 2 eyes, so you have high availability on the eyes, which is not really in line with our philosophy. We really want everything to be replicated, but we have a big problem with the octopus as a metaphor because it does have a single point of failure. That's not why we went away from using the octopus as our logo, but it's important to us that everything we do is completely scalable and has no single point of failure at all. I think a better metaphor for the technology might be a beehive, although there's still a queen bee. So I don't know, perhaps a coral reef or something. I'm still trying to figure out what the good metaphor is, or maybe I don't even need a metaphor. But I think the other thing that was an important design consideration for us was that it's a software-based solution, meaning that if you wanted to change the hardware out or put in faster hardware or slower hardware or solid-state disks here or spinny disks there or whatever you wanted to do, the technology was interchangeable because the software was separated from the hardware. And it gives people a lot more flexibility, and it also allows people to buy the cheapest hardware available. You can deploy Ceph on the least expensive hardware available, like say it's the end of the quarter, and your hardware vendor doesn't have any good deals, but another hardware vendor does. You can get your next petabyte for cheaper. You can do it because you can have a heterogeneous technology environment with the software solution. So that's thumbs up. The other thing that was really important was that the system is self-managing, and this is because hard drives are not going to be the technology for a whole lot longer. Spinny drives, if you look at it in the cave painting scope of the world, it won't be that much longer. But in the meantime, they're basically record players. They're little tiny record players inside of your computer, and they fail all the time. Like, they will fail. It's guaranteed to fail. And if you have a cluster with 1 million disks in it, that means that one disk is going to be failing 55 times a day. So it's really important that the system is self-healing so that 55 times a day when something goes wrong, it takes care of itself instead of needing human intervention to move data from one node to another or whatnot. So that's where Ceph came from. Ceph came from these ideological principles and these design philosophies. Sage went to college and built Ceph, and came back from college and decided to continue building Ceph because he thought he had something. So after the invention of Ceph at UC Santa Cruz, Sage came back to DreamHost, where he was a co-founder. DreamHost is an ISP it's a hosting company in Los Angeles, and DreamHost decided to continue incubating Ceph. To great results. The monthly code commits went up very, very noticeably at that point, and Ceph started popping up in other technologies like QEMU and OpenStack, and Ceph is inside the Linux kernel. And if you're on the marketing team at OpenStack, I'm really sorry about what I did to your logo. It's just to illustrate a point, but I know that that's a bad thing to do. But anyway, the point is that Ceph starts popping up in these places. All these integrations started happening even before there was any kind of commercial effort around Ceph. Truly community-oriented. So going back to this architectural diagram, I'm going to talk about each one of these boxes in a little bit of detail to give everybody an understanding of what Ceph is and how it works and how the pieces fit together. And the first one I'm going to talk about is RAOS, which is what everything else is built on top of. So RAOS is fundamentally an object store. And it works kind of like this. Let's say if I have a node with 5 disks. I need to put a file system on each of those disks. Ceph runs on top of a file system. And that file system can be ButterFS, XFS, or ext4. We believe that ButterFS in the long term is the right file system to run Ceph on top of, but it can be run with XFS as well in the short term as ButterFS begins to increase in stability. Then on top of each of these file systems, you run a Ceph OSD, which is an object storage daemon. We suggest that it's 1 per disk. It could be 1 per host if you want, or you could have multiple per disk, although I'm not sure why you'd want to do that. We really suggest 1 per disk, but it's flexible in the way that you deploy it. Then all of this on one node becomes part of a cluster. It gets added to a few other different types of nodes, most notably the monitor node, which is the big M there. And then a human being wanting to put an object into RAOS interfaces with the cluster as a whole, not with a particular OSD or a particular node, but interfaces with the cluster as a whole, and the object gets stored in a way that's transparent to the user. And you can scale this as large as you want it to be with commodity hardware. So just to review, the monitors, what they do is they maintain a map of the cluster. They understand which hosts are in and which hosts are out of the cluster, which hosts are up or down, which is distinct from in and out. It's different because in and out is less permanent than up or down. The monitors also provide distributed decision making. So you need to have an odd number of these because they talk to each other to figure out who has the correct cluster map. And if you have, let's say you have 3 monitors and one of them disagrees, you need to have the other 2 to have a majority. Also, if you have a split brain situation where you have a cluster split in half, you have 2 monitors on one side, 1 monitor on the other side. The side with 2 monitors is the canonical side of the cluster and will continue to operate as such because the monitors understand that they have the majority of the monitors. So it's important to have an odd number. These do not serve any objects to clients. They don't serve any data at all to clients. All they do is monitor the cluster. Also, when you mount the file system, you're mounting it with the host name of the monitor. So that's what the monitor does. The OSDs, 1 per disk is what's recommended, at least 3 in a cluster, because otherwise it doesn't really make a whole lot of sense. These actually do the serving of stored objects to clients. So these serve the data to who needs it. They also intelligently peer to perform replication tasks, which is part of that self-managing thing that I was talking about. And they support something really neat, which is called an object class, which I'm not going to go into all that much, but what it allows you to do is essentially have methods on the objects that you store. So, for example, when you put an image into your cluster, it can create a thumbnail automatically. And it's something that is a bit of an experimental feature because we're still figuring out exactly how much computing you can do on each of these OSDs without starting to dig into your the processor and memory and whatever required to actually store the data. So it's something that's kind of experimental now, but really, really powerful. So the next part of the component, or the next component of the architecture that I'm going to talk about is Liber AOS. And Liber AOS is kind of what it sounds like if you're a Unixy person and you're familiar with libraries. It's a library that allows you to build applications that interface with RAOS. So for example, if I have an application and it's built with Liber AOS, I can use that application to store a node into a cluster, and it's going to speak over a native protocol, which is a pretty quick protocol. It doesn't have a lot of overhead. It's super fast. So if you're building an application that needs to have very rapid access or very efficient access to a cluster, we suggest you use Liber AOS or any of its other language alternatives. There's alternatives for C and C++, Python, PHP, and Java. So that's Liber AOS, and it's really straightforward what Liber AOS does. And Liber AOS is the foundation for just about everything else that we built on top of Ceph. So the next component is called RAOS GW, which is the REST gateway for RAOS, which is compatible with S3 and Swift. So for example, if I have an application, I want to store an object into a cluster, I can have that application talk to RAOS GW, which is built on top of Liber AOS, which then accesses the cluster. And I can have multiple of these, right, because everything is distributed. There's no single point of failure anywhere. So the RAOS gateway, you can have multiple of them. You can put them behind a load balancer. You can do your standard web tricks to make sure that the RAOS GW is highly available, but the architecture supports multiple of them. And they speak a native protocol to the cluster, but they expose a REST-based protocol to the applications, which is compatible with S3 and Swift, which is kind of cool. They also support buckets and accounting. So this is the easiest way to get data in and out of a Ceph cluster if you're looking for application type storage. The next thing I'm going to talk about is RBD. So this is a block device built on top of RAOS. So for example, if I have a cluster and I have bits spread throughout my cluster that end up becoming a block device, I can run a virtualization container that has been built with libRBD and Liber AOS, and that virtualization container will present that information as a single disk to a virtual machine. So RBD, the RAOS block device, allows you to essentially stripe a virtual machine image across the entire cluster. And it can be a very, very large image or a very small image, but usually very large. And the virtualization containers that we support now. Oh, actually, I have that on a later slide. But the virtualization containers can be built with LibRBD, which allows them to have access to this block device. It also allows some really nice tricks. Like, for example, if I have one virtualization container that's running a VM off of a block device, I can actually move that virtual machine to another virtual machine container live, right? So because we're decoupling the storage from the compute infrastructure, live migration becomes something that's feasible and actually possible today. Also, if you don't want to do this in a virtualization context, you can use KRBD, which is a Linux kernel module, to mount a block device out of Ceph, right? So that's it's not built into a virtualization container in this example. It's built into the kernel of a client machine. So the RAOS block device allows you to store virtual disks inside RAOS. It provides live migration because of the decoupling of virtual machines and containers. It does striping across the cluster so that you can get that sort of distributed redundancy and performance. It has boot support for QEMU, KVM, and OpenStack Nova, and actually just a couple of weeks ago also CloudStack, and it has mount support in the Linux kernel. So that's RAOS block device. The final thing that we built on top of RAOS is Ceph FS. And I'll pause here for a second just to reiterate that all of these things, it's a unified storage platform. So in the same cluster, you can store objects, you can access those objects with REST, you can store block devices, and you can have a POSIX-compliant distributed file system in a single cluster. The same cluster, not separate clusters, the same cluster. And all of this has been built on top of LibRAOS. So if you want to build another application that uses Ceph to do something for tomorrow's needs, it's there architecturally. So Ceph FS is, as I said, a distributed file system. So for example, if I want to mount a file system, the first thing that happens is my client has to retrieve metadata from a metadata server. Something has to collect all of that metadata that accompanies a file, and also has to manage locking and permissions and actually manage the hierarchy itself. So a client will access the metadata server first to make sure that information is available, and then it will get the data from the OSDs directly. So the metadata server, it manages all the metadata for the POSIX-compliant shared file system, which means directory hierarchy. It also does all the file metadata. It stores its metadata inside RAOS, so the metadata server doesn't store it locally on its own disk. It stores all of its data inside the cluster, so that if the metadata server goes down, all of that metadata server's information is available to other metadata servers. It doesn't serve as it doesn't serve any file data to clients. That's another thing to know about it. And you only need this component if you're going to run Ceph FS. If you're just doing block devices or object storage, you don't need to run this component at all. So it simplifies the architecture to not have it. So I'd like to spend a bit of time and talk about what makes Ceph unique, what makes it different from all the other stuff that's out there. And the first example is sort of an exercise I like to call, how do you find your keys in the morning? So every morning I leave my house. I can never find my keys. Like, they're always in a different spot because I'm not, I'm not a creature of habit. I always put them somewhere different. But it's a good metaphor for how you store information in a distributed storage system. So if I'm an application and I want to store an object inside of a cluster, or I want to retrieve an object from a cluster, how do I know where to go to get that object? How do I know which part of the cluster to connect to? There are hundreds, maybe thousands of machines I could potentially connect to. And having an architecture where you connect to a single host and then it directs you is a single point of failure. So that's not allowed in our philosophy. So that's kind of a question. And one option is that you break up your cluster into multiple parts. Files that start with A through G, or directories start with A through G, or hashing something or whatever, but in some way you're breaking up your cluster and saying this stuff goes here and that stuff goes there and that stuff goes there. And that way, when you want to store a file, it tells you, oh, it starts with F. Let's go put it on that box, because that box is where all the files that start with F go, right? And that's what I always put my keys on the hook, right? And this is how most people live in their house. You always put your keys in the same place. You have a hook. You always know where it is. And when you want them, you go there and you get them. It's the same thing that happens in a lot of distributed file systems that are organized this way. The client knows where to get the data because that particular piece of data is always located in the same place, right, or the same kind of place. Maybe it's replicated or whatever. It's a little more complicated, but it's always the same place. The other way to do it is to have a centralized metadata server somewhere that you go ask, and it tells you, oh, if you want that, go straight, hang a left, hang a right, it's fourth machine from the top, right? And it tells you where in the cluster to get the information. It requires multiple round trips, and there's some concerns around a centralized metadata server being a single point of failure. But this is also a way that a lot of this happens. And this is what I call Dear Diary, today I put my keys in the kitchen. It's like writing down where you put your keys every time you walk into the house. And the only problem with this is, how do you find your keys when your house is infinitely big and always changing? Imagine having to figure out where your keys go when your house changes every time you walk into it, and it is infinitely large, right? That's the type of problem that Ceph ends up solving. And the answer to that problem, we believe, is called Crush. And Crush is an algorithm that is sort of at the core of how RAOS works. So with Crush, let's say I have a bunch of bits that I want to store into my cluster. The first thing that Crush will do is it'll hash them into a certain number of placement groups. And that's configurable. But in this example, there are 10 of them. And so after it's made its 10 placement groups, it runs those placement groups through Crush. And what you pass Crush is the placement group that you want to place, the state of the cluster, and a set of rules. And then Crush will tell you, based on that input, where in the cluster that data belongs. So it's a deterministic placement algorithm. It's pseudo-random, but it's repeatable. So it would take all of these items and spread them in the cluster in a way that was pseudo-random. It's very distributed. There's not a pattern around it, and so you get kind of an even data distribution. So Crush is the algorithm. It's pseudo-random. It's the algorithm that Ceph uses for placement. It ensures that data is evenly distributed across the cluster. It's repeatable and deterministic, so it'll always run the same way given the same input. And it's configured by rules. So instead of telling RAOS to always put, to have 10 different pools, and each pool is a different storage pool, and you have to always put these pools onto this node or whatever, the way you configure Ceph is you tell it, here's my general topology. I have this many rooms, this many rows, this many racks, this many switches, and the topology is configurable. So it doesn't have to be rooms, rows, racks, and switches. It could be anything. But then you can tell it, store this many replicas, and never put 2 replicas in the same room, or the same row, or the same switch. So it's a rule-based configuration. So for example, then, when a client wants to store or retrieve an object from a RAOS cluster, it will run Crush on that cluster, on that information, and Crush will tell it, oh, your information is on this node and that node. That's where it is, and it always runs the same. But there's kind of a challenge with this, and the challenge is what happens when you lose a node. So let's say I've lost this node with the red and the yellow square. These individual OSDs that make up RAOS are intelligent, and they peer with one another. So when that node goes down, the other nodes find out about it because they're constantly gossiping with one another, and they realize, uh-oh, the cluster map is updated. There's a new state in the cluster. So each node then recalculates the Crush algorithm on all of the data that they're currently holding, and they realize, uh-oh, to make Crush work in this new cluster map, we have to move this data from here to, or copy the data from here to there, the red square, and copy the yellow square over like that, right? So the nodes themselves intelligently reposition the data so that the next time somebody runs the Crush algorithm, the data is where it's supposed to be. So in this case, the Crush algorithm will tell the client that the object is located on the new node because the old one is down. So the next thing that makes Ceph unique and different from a lot of the rest is the way that it stores its block devices. So let's say that I have this virtualization container running a virtual machine out of a block device that's stored inside of Ceph. That's almost never the case, though. You never just want to run one VM. You want to run dozens of VMs, hundreds of VMs, right? And so the question is, how do you spin up these thousands of VMs instantly and efficiently? And that's somewhat difficult. And the answer is, with Ceph, you can do an instant copy of one block device to as many other block devices as you want. And in this case, I've created 4 copies of this block device, and all of them are taking 0 space because the copy is instant, but it's also thinly provisioned, right? So if I have 144 block, well, it's not really blocks like on a disk, it's just units. A 144 unit block device, and I copy it 4 times, it still takes 144 blocks. That's all it takes. And then, when my client begins to write information to this new block device, it begins to fill in the gaps. So if I write four block units to my copy, I end up storing 148 total. And then when clients go to read, if the data is inside the copy, it will read it from the copy. And if the data is not inside the copy, it'll read through it to the original file. And this is what we call it's thinly provisioned. So that helps people say, for example, if I want to spin up 1,000 VMs, I can copy my VM image 1,000 times. It happens instantly, and then I only start taking incremental space when new data gets stored. So the third thing that I think makes Ceph unique is its ability to manage a directory hierarchy without a single point of failure. One second. Without a single point of failure. So the challenge is that file systems require lots and lots of metadata. They require you to keep track of lots of information, you know, to assemble the hierarchy. And if you remember this graph of how the metadata system works with the Ceph FS, you'll notice that there are actually 3 metadata servers, right? Again, with Ceph, nothing is a single point of failure. So there are 3 metadata servers, which begs the question, how do you have one tree with 3 metadata servers, right? And the answer, or well, our answer, is that when the first metadata server comes online, it has control of the entire tree, right? It has authority for the entire tree. When the second metadata server comes online, it will take a portion of that tree. And since all of the actual metadata itself is stored inside Ceph, there's no data that copies when this happens. Another metadata server just assumes that responsibility. And as more metadata servers come online, you'll notice that they take sort of more equitable chunks. And this all happens dynamically. So as the load on the system or as the data requirements change, the metadata server will adapt and adjust and even allow you to have single hotspots, even down to the file granularity. So you could have one metadata server that is just responsible for managing locking and permissions on a single file, if that's what the cluster needs. And we call this dynamic subtree partitioning. So after saying all of this wonderful stuff, I have to backpedal a little bit. Almost everything works in Ceph. Almost. It's been in development for about 6 years. Having just launched the company Inktank, we're just starting to do some really involved quality assurance testing and performance testing. But here's where it stands right now. Right now, RAOS is awesome. It works very well. It seems to be very stable. We've had a couple of deployments that are achieving very good uptime numbers. The Liber RAOS is also stable. RAOS Gateway is stable, and RBD is stable, which means that there's one that's left out, and that's Ceph FS, which is almost awesome. And we're expecting that to be awesome probably early next year. The other backpedaling bit here is that this today is land scale. And the reason it's land scale is because when you write information to a Ceph object, it does the replication synchronously. So if you tell it to store 10 replicas, it has to go communicate with 10 other nodes before it comes back to the client and says, okay, I wrote the file, right? So, and that's how we keep the system sane, but it means that it works over LAN scale speeds or really, really scary fast LAN speeds. Sometimes we talk to people and they say, oh, it only works across the LAN, and they say, why? And we say latency, and they say, oh, well, we have, 2 milliseconds from here to the moon. And we go, oh, well, great, Ceph will work. So it's really more about latency than it is about the size of the LAN. So I have just a quick little slide on the current status of Ceph and Cloud Stack. And I chose this image because we really are at the beginning of the road with Ceph and Cloud Stack beginning to integrate. But there has been a good amount of work that's happened already. So this was just announced a couple of weeks ago. RVD support inside CloudStack, which allows storage of virtual disks using RAOS. It works with KVM only right now, and the volume snapshotting feature is not quite there yet, but it's definitely there. It requires the latest version of everything, so you have to build all of the latest stuff. And this is the information of this can be found on the mailing list, which gives you an idea about sort of where it is. We're also working on some guides and documentation and that sort of stuff, but right now it's in active development, and we're really interested to get people to try it and see if it works and see if it does what it needs to do. So that's my talk about Ceph. I'm available for questions if we have any time, and I will hand it over to, I guess, Geraldine to facilitate questions.
Great, thanks, Ross. So a high-level question for you. So can you explain the difference between Ceph and Hadoop?
I can. So Ceph actually came out of the HPC world when it was invented. It was invented primarily for the HPC use case, and that's where Ceph FS came from. Ceph FS being the part of the architecture that's not quite ready yet. So people have actually built HDFS sort of using Ceph as a drop-in replacement for HDFS, which it gives a little bit more scalability and gets around some single points of failure. But it's kind of experimental today. So I guess the major difference is, well, the first major difference is that Ceph is a storage platform and Hadoop is a distributed computing platform. The more apt comparison is Ceph and HDFS. And I think that there the differences are that Ceph is an object-based unified storage system, and HDFS is a very HPC-focused distributed file system. So I think that HDFS has got some things that they're very particularly useful for Hadoop-type workloads. Ceph is a little bit more general, but it can be used as a drop-in replacement for HDFS.
Great, thank you. Another clarification question. So how would one use RBD with Zen or Zen Cloud Platform? Is it possible? And how?
Yeah, so I think that what you want to look at, let me go back to that slide, what you want to look at is this message on the mailing list where a guy in our community named Vito, who's also in the CloudStack community, announced his integration, but I think it's only KVM right now. I know there's been a lot of work with libvirt, but unfortunately that's the information I've got at the moment. I think that we're going to spend an increasing amount of time with the Zen community figuring out where that integration is, and it's something that is still in development.
Great, thanks. So another question: can you explain the difference between Gluster FS and Ceph?
I don't know a whole lot architecturally about Gluster FS. I know that that Ceph has the object block and file on a single unified platform, and I think Gluster specializes in I believe file, and I think maybe they have block now. Unfortunately, I don't know a whole lot about Gluster. I know that Ceph's architecture, and especially Crush, was built to get over some of the architectural limitations that we find in Gluster. But I will also say that Gluster has had a lot more time in the market, right? So there have been a lot more people deploying Gluster and a lot more people using it. So I think it's the way that I kind of think about it is that Ceph is perhaps still a little rough around the edges, but I think it has a lot of architectural potential.
Great. So Ross, that's pretty much it in terms of questions. I'd like to thank you for taking time today to walk us through this drill down into the solution. And folks, do you have, Ross, a slide of how folks can reach out to you? Maybe we can put that up before we sign off.
Yeah, sure. Sorry, as I figure out how to operate my computer, one moment. Just scroll through my 136 slides.
There we go.
Everybody was very, very patient today. Thank you.
There you go. And you guys, so that is how you can reach out to Ross.